Welcome to this presentation on MDEOptimiser, our tool for searching for optimal models. I am Dr. Steffen Zschaler, and this is work with my former PhD student, Dr. Alexandru Bordesholm. Many engineering problems require us to find a solution that is optimal in some sense. Such optimization problems can often be encoded mathematically using three elements: a set of constraints that describe what valid solutions look like, a set of control variables whose values we can change to find different solutions of different quality, and a set of objective functions that evaluate the quality of a given solution. Optimization problems are pervasive in software engineering. Here are just some examples. Refactoring aims to change the structure of a software system without changing its behavior, but optimizing other properties such as maintainability and flexibility. Deployment aims to allocate software objects to the hardware so as to optimally use available resources. Program repair is an optimization problem aiming to find the changes to a software system that fix the most test cases. In feature configuration, finally, in software product lines, we often look for the configuration with the best performance or the smallest cost, and so on. The search space for optimization problems is usually too large to be explored exhaustively. For some problems, efficient exact optimization algorithms exist, but for many, we can best use a form of guided search that aims to explore the search space strategically, giving preference to parts of the search space more likely to yield good solutions. An example of this are so-called genetic algorithms. These take a set of potential solutions, make small changes to them using processes called mutation and crossover, and then keep the best solutions based on some fitness criteria. This process is repeated, often, until a population of solutions has been found whose quality is judged to be sufficient. There's a cost to applying these algorithms. Search algorithms need to be customized to the problem at hand, often requiring significant intelligence to derive good problem encodings and parameter tuning. This makes the application of these algorithms challenging in practice. In our research, we aim to make it easier to apply search-based optimization techniques by encapsulating the required expertise in MDE-based tools. The hope is that this will eventually enable domain experts to use optimization tools without having to worry too much about the underlying optimization expertise. So, what MDE techniques are we using? Well, first, we recognize that the syntactic structure of a domain-specific modeling language directly defines a search space. Every valid model expressed in the DSML is a potential solution to the optimization problem. We need to additionally differentiate which parts of a model are meant to be changed. That is, which parts of a model are the control variables and which parts simply contribute problem information. We may also want to specify which changes are allowed. We have found that this can be particularly powerful in guiding the search towards good solutions. There may also be additional constraints that aren't captured in the DSML directly. And finally, we need to provide a set of objective functions. Both constraints and objective functions are essentially queries over models, producing a Boolean or a numerical value. They could be expressed using a standard model query language, for example, OCL, but they can be any arbitrary computation, including simulation runs, and so on. A specific optimization problem is then defined by giving a model written in the DSML. Our tooling then uses all of these elements and produces one or more optimal solutions. To do so, we may choose an optimal problem encoding and an appropriate optimization algorithm to finally produce a set of optimal solutions that are, again, expressed in the original DSML. In fact, in MDEOptimiser, we use models directly as the problem encoding and apply evolutionary search. Here's a different perspective on this, showing the inputs, the internal process, and the outputs of MDEOptimiser. You can see that we are using standard metamodeling technology, the Eclipse modeling framework in our case, to capture the search space. We support OCL or Java implementations of fitness functions and constraints, and the changing of solutions is captured through a set of graph transformations, expressed using the Henshin graph transformation tool. This is an example of the specification of an optimization problem. We first specify the search space through a meta model and an initial problem model. We then describe what we're trying to find by defining objective functions and possibly additional constraints. What can be changed and how is captured next by referencing Henshin transformation rules. We will look at some examples in a moment. Finally, we have to define some control parameters for the search, and such as the search algorithm to use and when to stop the search. Here's an example showing how to use MDEOptimiser to refactor class diagrams. These are the additional artifacts referenced from the specification we've just seen. In the top left corner, we see the meta model of a simple modeling language for specifying class diagrams. We could also have used the full UML specification here, for example, but are keeping things simple for the purposes of this presentation. The top right corner shows an example of a Java-based implementation of a fitness function. This function aims to minimize the overall size of a diagram. Finally, at the bottom, you can see a Henshin rule, showing how a new superclass can be introduced to capture commonalities between multiple classes. These rules can capture significant domain knowledge, making the search much more efficient, but they can also be a bit difficult to write correctly. Fortunately, for many scenarios, we can ask MDEOptimiser to generate these rules for us from a much simpler and declarative specification. Here's an example specification of an optimization problem where we haven't explicitly defined any Henshin rules. Instead, we declaratively state that the search should explore creating and deleting instances of the class metaclass and adjusting the associations between these instances and the remainder of the model. From this, MDEOptimiser automatically generates appropriate rules. It turns out that generating the rules automatically can also make the search more efficient. Here we see the results from experiments showing time on the x-axis and quality on the y-axis, where higher values are better. The cyan line shows search with the generated rules, while the red line shows search with a set of manual rules created independently. For this example problem, the generated rules are consistently more efficient than the manual rules for the different example problems explored. So here we see MDEOptimiser running in the Eclipse IDE. MDEOptimiser is an Eclipse-based tool, but optimizations and searches can be run directly from the command line. However, just for creating the specifications of an optimization problem, it is easier to do that within Eclipse at the moment. So here we see an MOPT file, which is the XML that we used for specifying search problems. You can see up here there's the description of the overall problem. We're saying what the meta model is and what the specific problem model is. And we can see the meta model referenced is this one here, which is the class refactoring meta model that I just showed on the slides as well. And there is an example input model here where you can see that this input model contains lots of methods and attributes, but currently does not contain any classes, because the problem that we're trying to solve is we're trying to find an optimal set of classes and allocations of methods to and attributes to these classes that produces has good maintainability properties, basically. Our goal is then described here in more detail, and in particular we're first defining some additional constraints, saying that every feature needs to be in a class in a valid solution, and then we're defining our objective function here by referencing out to a Java-based implementation of this fitness function, which I have open here. So let's have a look at this. You see the main thing about any of these fitness function implementations is to implement this compute fitness function here, which takes in a model and produces a double value that represents the current quality, if you wish, of this given model. And what we're going to do here is we're going to calculate a so-called CRA index, which has sort of a relatively lengthy calculation here, but effectively comes down to calculating the cohesion and calculating the coupling that's currently represented in our model, and then sort of producing a single index, a single quality index from those two values. But what I'd like to point out here, what's important to note here, is that actually we could do anything here, right? Anything that we can do in Java, anything that takes a model and produces a number from that model is a valid thing to do here. So we could, for example, run a simulator, an external simulator, to check for the quality of this particular given model, which is a useful thing to be able to do in certain problems. And then if we go back to our MOPT file here for a moment, then we say, how are we going to search? And we can see here, as I said, we're going to search not by explicitly having to specify any rules. We're just saying what part of the overall model should be changed. And we're saying, well, we're changing any instances of this class, meta class, and any of the links that go in and out of it, which are basically the associations that describe which attributes and which methods are contained or encapsulated in which classes. And from this, MDEOptimiser will generate the appropriate rules for us that it will then use during the search. And then we have to, down here, as I said, specify a little bit about what search algorithm to use, etc. But I'm not going to explain this in too much detail. If we just run this here, running the search is a little bit boring. We'll see something scroll past in the console. And it'll take a little bit of time, so we're going to speed up the video at this point briefly. As I said, we have run the search now directly from Eclipse, but as I said before, we could also run the search once we've defined our problem using all of these tools here. We can also run the search directly from the command line, so you don't have to run Eclipse just to run a search. Let's explore a little bit what the results of this search have been. MDEOptimiser has left these results for us in this MDO results folder here. The first thing I want to look at is these operators that MDO has generated. So as I said, MDO has generated these henshin operators for us, these little transformation rules that describe how it searches the search space. So let's open one of those up, and I'm going to just actually quickly generate a diagram file from this. Yes. So we can look at the rule graphically. And so here we are. Let me just fix the layout of that a little bit. Okay, so normally we would not look at these rules, but just use them. I'm just showing this rule here briefly so you get a bit of a sense for how things work. So this is a transformation rule that says we're going to look at a feature here, and we're going to pick an existing class. So there are other rules that will create these class objects. And here we're going to look at a feature, and we're going to look at an existing class object. And what we're going to check is first that this feature is not contained in, already encapsulated by, any other class object in our model, and that it's also not encapsulated by this class that we've picked at random here. And if that's not the case, then this rule creates these two new links here, specifying that this feature will now be encapsulated by this class that we have picked. So this is one of those operators, and basically that's what MDEOptimiser does during the search, is apply these rules, apply these small transformations, check whether they have improved the quality of the solutions, and keep the best solutions around, and continuously keep searching for better solutions. So let's look at what it's found. So here is a brief sort of text file that sort of summarizes the key results, and it's sort of found a solution with a particular CRA index here. So that's a reasonable value for this particular problem. It gives us some additional information, but perhaps more interestingly, it gives us the actual model here. So let's open that up briefly. remember the model that we fed in did not contain any classes, it just contained methods and attributes. So if we look into this model here now, we'll see that it now contains a number of classes. It still contains all of the methods and attributes that the original problem model contained, but it now contains these various classes here. And let's just look at one of these, and we'll see down here that now this class now encapsulates a number of those methods and attributes. This class captures some others, and this probably captures all the rest in this case. And so this is the optimal solution that MDEOptimiser has been able to find in this search. We are very interested in working with you. If you have interesting optimization problems, please get in touch. This will also help us further improve the tool. Some challenges that we're already aware of and have ideas that we would like to explore further include scalability to very large models and using other algorithms apart from evolutionary search. The vision is that eventually MDEOptimiser would become a tool in which an optimization problem can be described without the need to worry about finding an efficient way of finding the optimal solutions. Thank you for your attention. I would also like to thank our collaborators, Stefan Zschaler, Daniel Struber, Jens Kosiol, Gabriel Tenzer, Robert Bill and Manuel Wimmer.